Hi, everybody. This is Mr. Youngren, and welcome to Unit 3. In this unit, we're going to be writing equations of our form functions. And we're going to be doing this in a number of different ways. Last lesson, you guys learned how to write them from some things that we're familiar with, so using tables and being able to take those tables and then turn them into one of our equations. What we're going to do in this lesson is we're going to see an application that represents one of our four functions, and we're going to see if we can't identify based on the application what kind of function we're dealing with, and then can we use that equation or build an equation and then put that to use to either help make a prediction or help solve some sort of real world situation. So again, standard 7 is writing equations of functions from context. You can see that we're doing this for all four of our functions. Below this is just your key. This is a good thing to refer to as you work through this, so that if you identify a given function to be linear, absolute value, exponential, or quadratic, you can look here and say, okay, what should that equation look like, right? This is something we want to continue to work on as we keep working with all four functions. So let's jump into a few examples. And one important thing when we get to these applications is to what I call take the math away from the words. I think oftentimes students, they see these words and it's tough, right? Because you're having to read the problem and then process, okay, how do I bring the math into that? Well, we're going to see if we can't take the math away from that. So what we're going to do is we're going to read the problem, and anytime we see a word that seems math related or one that we think can help us either build the equation or solve a problem, we're going to identify that by either underlining it, or if you have a highlighter, that'd be really awesome to use as well. Right, so it says, due to a drought, the canal from a reservoir is open so that the reservoir is lowered. That's important, right? It's starting that it's lowered, right? Anything that has to do with growth, that's math related, is lowered to meet the irrigation needs for farmers. The level of the water is being lowered, again, we're seeing that word lowered, by 15 feet per day, right? Knowing the amount at which it's lowered is helpful. Until it hits its lowest point, low point, that's important, at 85 feet after 5 days. Then the water level begins to raise at the same rate as it was being lowered. Okay, so right, anything that has to do with growth or position, right, anything that I might be able to use in an equation, I've identified. So now we're thinking about, okay, what four functions? Well, there's a really important word here that gives it away, or at least allows us to start to narrow it down. And the first thing is that I see the same rate. Right? So it's being lowered at the same rate, but also the water is rising at the same rate. So telling me it's constant, right? So we have two functions that are constant, linear absolute value. And so really what we need to decide is there a turning point? Well, if I made just like a quick sketch of this graph, right, where our y-axis was the water level and x was time, right, it says that it's being lowered until it hits its low point, then it goes back up. Look what we just did. We modeled what that looks like. It does not look like one of our four functions. It looks like absolute value, right? And the whole point of that was to identify that we have a turning point. Now that turning point, if we look at the graph, we can see it's the lowest point on the graph, right? There's nothing below that. And there's something about that we identified in the word problem, is that that low point is at 85 feet after 5 days. But look what else we've done. We've got the exact location of the turning point. We've also got the x coordinate, right, relating to time. Anytime that a problem deals with any sort of time, whether it's days, minutes, hours, weeks, years, that's going to be your x coordinate. And then the other variable is your y coordinate. So this turning point is at 5,85. And now we have all of our information, right? We know the rate, and we know the turning point. So what type of function is this? It's absolute value. This ink is running out. Let's switch over. Absolute value, because the rate is constant. And there's a turning point. So now write an equation that represents the situation. Well, one thing that we needed to decide, right, with absolute values, we know that we increase and decrease, right, or decrease then increase. So we need to figure out, do we want that A value, right, which really works as our slope, be positive or negative? And the way that we're going to do this is something that I've already done, and that's to make a graph, right? What the graph helped me do is decide, okay, since it started to lower, I'm lowering the water level as the time is moving, right? Or as the time is passing. So I'm able to go down, hit that low point, and then go back up. This tells me right here, since the graph opens up, oops, A is positive, right? So now we know the rate of change is 15. We just needed to decide, is it plus or minus, right? Because we don't use both in the equation. We only use the sign in which is the graph opening up or is it going down. So our equation is y equals, that's 15, absolute value of x minus 5, right? Time was positive, so we got to switch the sign. Always doing that with every one of our functions. And then plus the y coordinate of 85. And so now what will the water level be after day 7? Well, our x value is the number of days. So I can take 7. We can plug or sub in for the x. So literally take the x away, put 7 in the equation, go ahead and solve it. So this is where we'll refer back to PEMDAS. 2 plus 85. Remember, even though it's positive, it needs to stay positive, but we're going to show that we take the absolute value by turning into regular parentheses. Right, so that's me taking the absolute value, even though nothing changed. We still want to keep that in mind just in case it had been negative. And 15 times 2 is 30 plus 85, and y equals 115. So what will the water level be after day 7? We're not going to answer that with y equals 115, right? That doesn't make any sense. So let's put some context on it. So the water level will be 115 feet after day 7, right? So as long as we're taking that value and putting it back into context, that's what we're looking for. Right, well, let's do one more together and let you all work from there. Right, so you want to buy a Tesla Model S. They offer a payment plan that requires $6,000 when you purchase the car. Again, as I'm reading this, I'm like, okay, what's important there? So a payment plan that requires $6,000, right, meaning we are giving $6,000 to the dealership once we buy the car. And then we have to pay a monthly fee of $1,050 each month to work towards paying off the rest of the car. Right now, this is pretty much how it goes when you do purchase a car, that you may not have all the money up front to be able to purchase the whole thing. So dealerships work out payment plans with you, and this is one that it kind of models. Now, one thing that they do is they do add some interest on it. So there's usually a percentage, and it's more an exponential equation. But for the sake of this problem, we're just going to go by the information provided. So again, we identified that we excuse me, had to pay $6,000 up front, and then $1,050 each month is what we're going to continue to pay until the car is completely paid off. So what do I know? Well, how much is going up by is $1,050 every single month, right? That is not changing. Okay, so again, if we can make a graph, this really helps us understand what kind of function are we dealing with. Well, our x-axis is still going to be time, which is months in this case. And then y is our other variable, which is amount paid. So it starts at 6,000, and then it's just going to go up at that 1,050. Well, if it's going up by the same amount, right, that creates a straight line because it is constant, and there's no sign of it turning or having a turning point. So this is going to be linear. That's because the rate is constant. And no turning point. Write an equation to represent this situation. Well, again, we can look back. I'm like, okay, what do we know? I know the rate, that's m, x minus x1, right? That's the start, that's the x coordinate of our start, and then plus y1. So look at this, I'm like, you know what? The start is at 0 months when you pay this. So I could write x plus 0 in parentheses, right? But it doesn't really make it doesn't change. Adding 0 doesn't do anything to the x. So really all we have here is a y for our start. And this looks more like our y equals mx plus b and not the point slope form. So our equation is y equals, the slope will always come first no matter what. And then that's x and then plus 6,000. Right? And this really represents what's going on. Every time we go a month, we're going to fill in a value for x, multiply it by the amount we pay per month, and then add on that initial fee. So how much will we pay after 12,000? Well, I'll go ahead and set this up and let you work it out from there. And we'll go ahead and do it real quick. So again, we're going to take 12, sub it in for x. So then we can take 1050 times 12. Again, keeping order of operations in mind. That's why we're multiplying first. We get 12,600 plus 6,000. Just add 6,000 onto that amount. We get that we have paid $18,600. Again, make sure that we are writing this in context of the problem, right? It is the amount paid. All right, so we want to use these same strategies as you work through all of your other real world situations. Okay, work on a graph, see if you can identify what your x variable, what your y should be. And then thinking about rate of change and whether or not it has a turning point is going to help you identify which type of function. Right, thanks for watching. Make sure that you get your video checked and complete. Have a great day.